Hello, everybody. Let's start our lecture. And the topic of the lecture is Skorokhod space. We discussed convergence of stochastic processes in the space of continuous function. However, a lot of processes does not have a continuous path. For example, Poisson process, it have jumps, and we need to introduce some metric on the space of discontinuous functions. A lot of processes have so-called cadlag modifications, so their trajectories are continuous from the right and have left limits. So this is just notation cadlag. It's from French continue à droite, limit à gauche, and translation to English is continuous from the right and left limits. And I would like to introduce some metric on this space. And this space is quite nice because if processes have trajectories that are continuous from the right and left limits, then automatically say supremum of the process on certain interval or infimum or integral are well-defined random variables. And for such processes, supremum, for example, is equal to supremum taken over rational numbers. Okay, so let's start with definitions. Let D 0 t be a set of functions f from 0t to r such that for every t in 0t, f is continuous from the right. And for every t in, excuse me, yes, and for every t from 0 to t, 0 is not included, there are limits from the left. And such functions are called cadlag functions, so it's easier to write than to say cadlag instead of continuous from the right and having left limits. Well, I exclude here t and 0 in this assumption because function f is not defined for negative s and are not defined for t greater than t capital. Well, and spaces t0 infinity is defined similarly, and if we wish to discuss, say, vector-valued processes that are continuous from the right and limits from the left, then I will write t0t, say, rd, for example. This is just notation, or if they take values in some metric space, then metric space E, then I write E here. And now I wish to introduce some metric on this space. Well, the first natural choice is supremum metric For example, we may define the metric rho infinity between f and g is supremum over all t in 0t f of t minus g of t. Well, this is symmetric, so it's not complicated to show. However, the space of cadlag functions with this metric is not separable. Well, and it's easier to study separable metric spaces because, for example, you may apply Skorokhod representation theorem, Prokhorov theorem, and many other nice theorems. So work only in separable spaces. And another motivation is this. Consider the following function, indicator function. Okay, it's 0 before certain point t star and 1 and 1 for all other t. And well, in some sense, it's natural to suggest that this function, so indicator, so this indicator is close to this red function if this point is close to this one. And distance in supremum norm is 1 between these two functions, so we don't have convergence. And Skorokhod proposed a few natural metrics in the space of cadlag functions that make this space separable. I will discuss only one metric that is called J1 metric. So usually people study convergence in this metric. However, there are three other.
Excuse me, is it my problem with sound or
No, I don't hear you also.
You too.
Do you hear me now?
Now we hear.
Oh, okay. Occasionally I pressed a button on my headphones. Okay, so now I'm going to introduce Skorokhod metrics in this space. And by lambda, I denote the set, so lambda or lambda 0t is the set of all functions from 0t to 0t such that lambda is strictly increasing, continuous, lambda of 0 is 0 and lambda of t is t. So lambda is transformation of the segment 0, 3. So it's bijection and yeah, so continuous bijection 0t to 0 t and two assumptions that lambda of 0 is 0, lambda of t is t, and Skorokhod defined the following function. D the following distance between two functions f and g. It's infimum over all lambda in this space of maximum or supremum t in 0t f of lambda t. So we transform the time of the first function and subtract the second function. Okay, and that's all. And the statement is that D is a metric. On D0t. And space D0t with metric D is separable. Is separable. Okay. So let's discuss informally. What does it mean? Assume that you have two functions, f and g. So this is f of t, and this is g of t. So we make some time transformation of function f. We obtain this function in a transformed time, and then we consider supremum norm between transformation of f and g. And excuse me. Infimum over all. I forgot, excuse me, I forgot to write, and maximum of this value and of this value, maximum t in 0t, lambda t minus t. So maximum of this, and then we take supremum over all lambda. So metric d between f and g is small if there is transformation of 0t, which is close to t, so small transformation of identity, such that if you make this small transformation, then supremum norm between f and g becomes small. So if we consider this picture, then probably we have to make a transformation of this interval such that this point be here, and then this jump, so the time of this jump will be at this point, and then we consider supremum norm after this transformation of time. Let's consider one simple example where functions g and f are indicators. Let f of t be indicator of T1 T of T, and G of T is indicator of T2 and T. This point is T1, and this point is T2. Well, let's lambda of T be the following function. So it's easier to make a picture than to write the formula. So T. So function lambda of T should start at 1. It should end at T. And let lambda be linear function on 0 T1. And the value at T1 of lambda assumes that it's T2. So linear function here and linear function here. Equation. What is supremum over all t in 0 T? F of lambda T minus G of T.
0.
Yes, it's 0. It's 0. And what is maximum over T in 0 T capital of lambda of T minus T, where this maximum is attained? Yes, at T1. So difference is maximal is here, and yes, T2 minus T1. Well, absolute value of T2 minus T1. We don't know, is T2 greater than T1 or not? Well, in this picture, it's greater. So I know that the distance between F and G is less than or equal to T2 minus T1. Another question. Is it true that, well, I give you concrete function lambda such that maximum of this and this is equal to T2 minus T1. But definition of Skorokhod matrix is infimum over all lambda. The question is it true that this distance is equal to T2 minus T1? Well, and assume for simplicity that T2 minus, assume for simplicity that distance between T2 minus T1 is less than or equal to 1. The answer is yes. If you have this, then you have equality. Indeed, if lambda of T1 is not T2, then supremum over all T in 0 T indicator f of T of T1 T1T and indicator of T2t is just 1. Well, when we transform indicator, then the transform function is indicator again. So if this moment of jump is not here, then the distance between transformation of this function and this function is equal to supremum of difference, and it's 1. It's attained in all these points between this point and lambda and f of t1. So maximum.
I'm
Yes.
sorry, maybe you meant indicators from lambda, not from f.
Oh, lambda. Yeah, sure. Lambda of t. Thanks. Lambda of t. Yes, you're absolutely right. So maximum of supremum distance and between transformations of functions and of these is greater than or equal to 1. So this distance is really difference between T2 and T1, and we see that if well, from this we may conclude that if T2 is close to T1, then indeed the distance between two indicators is small. But let us return here and let's analyze the Skorokhod matrix. Well, I will not prove that D is a metric. Here you may find proof, for example, in Billingsley book. Convergence of probability measures, for example. But let us discuss the following. The first, is it true that DFG is 0 if and only if axioms of matrix, if and only if F is equal to G? Well, it's really easy to see that this direction is obvious. Just take lambda of t is t, then you see that this is 0, this is 0. Other direction is also not complicated, so please think about this. The second assumption is symmetricity, so that d of f and g is equal to d of g and f. Well, actually, it is not so clear that this function is symmetric. And if yes, then why? But let's discuss this. For example, supremum of f of lambda of t minus g of t and t in 0t. Well, function lambda is strictly increasing, is continuous, so there is inverse function, and the inverse function is strictly increasing, is continuous. Well, and since lambda of 0 is 0, then the inverse function also satisfies this property. And inverse function of t is t. Well, and inverse function also maps 0t to 0t. So inverse functions in the inverse function also belong to this class. And let me denote, so introduce notation. Let S be lambda of t. So t is inverse of S. And if t in 0t, then S in 0t again. and T in lambda is bijection between 0t and 0t, then if S in 0t, then T also belongs to 0t. Hence, this difference is equal to supremum over all S in 0t. F of lambda t is f of S minus, and what is T? T is inverse. And if so, infimum over all lambda in this set is equal to infimum over all this function in this set. And actually, so this is supremum G of, okay, let me denote lambda tilde is this lambda tilde of t minus f of t in 0t. Oh, so we see that this function is equal to this supremum is equal to this supremum, and infimum of this is equal to infimum of this. Well, and similarly, you may show that maximum over all t in 0t lambda of t minus t is equal to maximum over all t, the inverse function, and t. Okay, and that's all. That's all. So this function d is really symmetric, and well, and triangle inequality is more complicated, and I will skip this reasoning. So please look details, for example, in this book. You may also ask me the following question. Here I write maximum, here I write supremum. I did it on purpose. Lambda is continuous function, so maximum is attained. And f and g are cadlag functions, so I'm not sure that maximum of cadlag function is attained. Indeed, the function may be like this. So this is cadlag function, and maximum is not attained. Well, another question you also may ask me, is it possible that supremum is infinite if function is cadlag? Well, no, the answer is no. Cadlag functions are bounded on any compact set, so this is an exercise. And now I would like to discuss some properties of convergence. And the first one is what is the relation between convergence in Skorokhod metric and uniform metric. And the first statement is the following. If the sequence of cadlag functions Fn converges uniformly on 0t to f as n tends to infinity, then Fn converges to f in Skorokhod space with Skorokhod metric. Well, the inverse is not true, and counterexample is indicators. So if T2 converges to T1, then indicators converge in Skorokhod metric, but they do not converge in uniform metric, and distance in a uniform metric is always 2 if T2 is not T1. However, it can be shown that if Fn converges to F as n goes to infinity here in Skorokhod space, then the limit function is continuous. Then Fn converges to F uniformly in 0t as n tends to infinity. Well, let's prove the first part, and I wish to recall this definition. Okay, this definition. Well, a question, how to do it? For example, you may select some sequence lambda n such that Skorokhod distance is small.
Well, we know how to control this first distance between F and
Yes, so uniform
G.
distance is supremum. We know that supremum over all t in 0t, yes, okay, Fn of t minus f of t converges to 0 as n tends to infinity. Okay, and how to control this?
I think that Skorokhod distance is always lesser or equal than uniform distance.
Why?
Because we can take in this infimum we can take lambda t is t.
Absolutely right. So if we take lambda t is t, then this maximum, okay, let's take lambda t is t, then maximum of lambda t minus t is 0, and f of lambda t is just f of t. You're absolutely right. So this is 0, this is f of t minus g of t, and
The distance between Fn and F, right?
yes, and this
We don't have
infimum.
G.
No, I say in this definition.
Okay.
So this is always less than or equal to supremum of f of t minus g of t in 0t. So Skorokhod distance, Igor was absolutely right, is less than or equal to uniform distance between f and g. So if the uniform distance converges to 0, then Skorokhod distance, which is less than this one, also converges to 0.
So we actually proved something a little bit stronger, yes? Because
Yes. Yes. We prove a little bit stronger result that this matrix is less than or equal to this metric. Yes, and if one metric is less than another one, then this is a corollary. Okay, and now let us try to prove the second part, and the second part of the statement, and we assume that the limit function is continuous. So what do we know? We know that d of fn and f converges to 0 as n goes to infinity. So infimum over all lambda of let me correct this, of distance between fn and f, and this converges to 0. Hence, I can select, for every n, I can select lambda n, a function, such that distance between fn and f is close to this infimum up to, say, distance 1 over n. So I can select a sequence lambda n functions from lambda such that limit as n goes to infinity, maximum of supremum over all t in 0t fn of lambda n of t minus f of t, and maximum of lambda n of t minus t. Converges to 0. So actually, this means that lambda n converges to t uniformly. That lambda n of t converges to t uniformly on this interval. And we need to prove that fn converges to f uniformly, so I need to estimate supremum over all t in 0t fn of t minus f of t. Okay, I know that d is distance, so we discussed that I may write fn of t minus f of lambda n of t in the definition, and I have this. So let me add and subtract f of lambda n of t, and use the fact that absolute value of sum is less than or equal to sum of absolute values. So fn of t minus f of lambda n of t plus f of lambda n of t minus f of t. And we know that supremum of sum is less than or equal to sum of supremums.
I'm sorry, when we
Yes.
took lambda n
Mhm.
and get it from fn to f,
No, so Igor, I say that we proved today that distance between Fn and F is equal to distance between F and Fn. And we may write...
okay. So sorry, I thought we made
no,
this trick
no,
with
no, no, no. So I may write this definition of distance, like f of lambda
yes,
n
yes.
minus, or you may write here the inverse function, but I don't want to do
Okay,
it.
thank you, it's clear, thank you.
And okay, the first supremum converges to 0 because Skorokhod distance converges to 0. And f is continuous. So f is uniformly continuous. And lambda n converges to t uniformly. So this supremum also converges to 0. Okay, so let me explain this. So I need to show that for every epsilon greater than 0, there exists a number such that for n greater than or equal to n0, this supremum is less than epsilon. So what does it mean that f is uniformly continuous? This means that for every epsilon greater than 0, there exists delta such that for every st in this segment such that s minus t less than delta, we have f of s minus f of t less than epsilon. And now I have this, so I can find a number n0 such that for n large enough, supremum over all t in the interval, lambda of t minus t less lambda n of t minus t is less than delta. But if lambda n of t minus t is less than delta, then difference of f, then this absolute value is less than epsilon, and so supremum is less than or equal to epsilon, and we have convergence of this sum to 0 as n goes to infinity. So supremum the uniform distance between Fn and F converges to 0 as n tends to infinity. Questions? Okay, if no, let's make a short break for 10 minutes. Okay, let's continue to discuss convergence in Skorokhod space D, and I wish to give you few exercises. At first, prove that functions supremum, so prove that functions from D to R is measurable. Well, and in a Skorokhod space of cadlag functions, we consider Borel sigma algebra. The second question, is this function continuous? So is supremum continuous function from D to R? Is it continuous? And the second exercise is similar. what about integral? So prove that this function is measurable, and the question is it continuous? Is it continuous function from D to R, where we consider Skorokhod metric on the space D? F of S is measurable. The second exercise is the following. Prove that the space of continuous function is closed in, so this is subset of space of cadlag functions, and prove that this set is closed in D0 T. So this means the following. So if Fn are continuous, and if Fn converges to F in the space D, so I will not write 0T capital and like metric D, so I will write converge in D, then F is continuous. Well, and we know, by the way, that if the limit is continuous, then moreover you have uniform convergence. So two corollaries are the following. It's impossible to approximate discontinuous functions by continuous one in this Skorokhod metric. So these are bad news, and good news that the space of continuous functions is closed, so it's measurable. And another question, prove that step functions, the set of step functions is dense in D, that the space of step functions is dense in the Skorokhod space with Skorokhod metric. And when I say step function, this means that there is a finite number of points T1, T2, T3, and so on. Tn is T capital, such that function f is constant on each interval. And one more exercise. Prove that the Skorokhod space is separable. And hint for this exercise is prove that you may approximate any cadlag function by step function in the uniform topology. And hint here is use previous exercise. By the way, if you consider uniform metric, then is the space of step functions with uniform metric separable or not?
Can you please say again, a space of what?
Of step functions with uniform metric, is it separable or not?
Yes. Yes.
No, this is not true. If you consider even indicators, then the distance between every two uniform distance between two indicators is 1. And
Okay.
so if you consider uniform metric, it is not separable, but Skorokhod metric, yes. And for example, dense set here is the space of step functions where these numbers are rational and these heights are also rational numbers. Okay, and now well, one more maybe exercise, but we can say that it's corollary from the previous theorem that states that if Fn converges to F in the space D and Gn converges to space G in D, and F and G are continuous functions, then Fn plus Gn converges to F plus G in D. Well, indeed, we know that if the limit functions are continuous, then the limit is uniform. So if you have convergence in D, then you have the uniform convergence, and if Fn converges to F uniformly, Gn converges to G uniformly, then the sequence converge to this, then the sum converge to the sum uniformly, and so in D. I will use this exercise and solve the following problem, or solve the following or answer the following question. We know the Donsker theorem. Well, let's consider random walk psi1 plus psi2 plus psi n. I remember that we extended this random walk by linearity to all non-negative real numbers, and we know that S of nt over square root of n converge in distribution to a Brownian motion if these random variables were mean 0 and variance was 1. Well, and converges in distribution in the space of continuous functions with the uniform metric. And a very natural question is this. Okay, let's consider this sequence. F of S and T, integer part, over square root of n. So we do not extend the function by linearity, but consider like step functions. And so on and so forth. And we consider the same scaling, and the question is it true that you have convergence to a Brownian motion, but in Skorokhod space, where topology is generated by Skorokhod matrix? And okay, let us analyze this problem, and let's consider what is the difference between this and this. What is supreme over t in 0t? or, well, for simplicity, let's consider t in is 1 of s psi n t linear approximation over square root of n minus s psi integer part of nt over square root of n. Well, it's easy to see that the maximal distance does not exceed or equals uh, maximum the maximal jump maximum of psi k divided by square root of n, where psi k is such that and okay, and k between 0 and n and n and n minus 1. Okay, and n minus 1. We know that if you have a sequence of independent identically distributed random variables such that the second moment is finite, then maximum of psi k of n random variable divided by square root of n converges in probability to 0 as n goes to infinity because expectation of the second moment is finite. So we see that this sequence and this sequence are close in supremum norm. And now, okay, and now, for example, we may apply Skorokhod representation theorem. And construct sequence of copies of these random walks defined on the same probability space such that these processes converges uniformly to Brownian motion, well, to copy of a Brownian motion almost surely. And then, well, we know that this distance for copies converges to 0 in probability. So S psi n t integer part over square root of n, we may represent it as this linear function plus difference. This converges almost surely and uniformly to a Brownian motion. This part, absolute value of this part, converges in probability to 0. So this means that supremum of this converges in probability to 0. So the difference between this and this, so supremum t in 0, 1, 0, 1 converges in probability to 0. So we have convergence of these copies to these in probability in the space D. So as an integer part of nt over square root of n. So these processes converges, well, uniformly in probability. So they converge in probability to b tilde of t if we consider these processes as random elements with values in Skorokhod space with Skorokhod metric. And we know that convergence in probability implies convergence in distribution. Okay, copies converged in probability, so originals converge in distribution to the Brownian motion, to the copy of Brownian motion. So Donsker theorem is true if we consider step approximations and Donsker scaling, and if we consider space of cadlag functions instead of space of continuous functions. Okay, questions? If not, let us discuss important examples of cadlag processes.
Please, can you return back first for a second, please? Thank you. 1 second. And this weak convergence in D, yes?
In D, yes.
Okay.
In D, well, this is discontinuous process. Yes, so yes, convergence in D with topology generated by Skorokhod metric.
Okay, thank you.
And the first important example is Poisson process. And let me recall a definition. A cadlag process, cadlag process means process with cadlag trajectories. Process n of t is called a Poisson process with intensity lambda. If first it starts from 0, second n is a process with independent increments, third n is a process with stationary increments, where the distribution of increment is Poissonian with parameter lambda times t, where t is the length of this interval from S to S to T. For every S and T non-negative numbers. Okay, and so I hope that you have heard about Poisson process, and let me make a picture of the graph. So at the beginning it's 0. So the process is non-decreasing. The jumps of this process are equal to 1. So this is 1, 2, 3, and so on and so forth. And it can be proved that the waiting time of the first jump has exponential distribution. The time between the first jump and the second also has Poisson exponential distribution, and so on and so forth. So, and the statement is that psi k, where they are defined like this, are independent, identically distributed random variables with exponential distribution with parameter lambda. So if n lambda is Poisson process, then and psi are constructed like this, then they're exponential. And the second part, if you take are independent, identically distributed random variables with exponential distribution, and if you construct the process like this, and lambda of t is n if t in xi1 plus xin, xi1 plus xin plus 1, and 0 if t is smaller than xi1, then and lambda is a Poisson process. I will send you reference to a textbook where you may read the proof of the following fact. And now let us discuss. So this is the last question for today. Let us discuss relation between the process n of t and random walk s psi of n. You see, we have sums of xi1 plus xi2 plus xin and so on and so forth. So they maybe there is a formula that is related as xi and this process n lambda. Are there any ideas? Well, if not, let's make a picture. So this is n, that is s psi of n. So s psi of 0 is 0, s psi of 1 is psi 1, f of psi 2 is psi 1 plus psi 2. Okay, let me make this picture. Then psi 1 plus psi 2 plus psi 3. And now look at this picture and this picture. So this is psi 1, this distance is psi 2, this distance is psi 3. See, 1 psi 1, 2, 1 psi 2, 1 psi 3, and here psi 1, 1, psi 2, 1, psi 3, 1, and so on and so forth. So in some sense, Poisson process is inverse for this sequence. And it seems to me that n lambda of t is infimum over all s such that s psi s is no f psi s. Okay, let me write integer part is greater infimum over all n. Okay, that s psi of n is greater than t and minus 1. Indeed, if t is here, then infimum of n such that s psi of n is greater than 0 is 1, because s psi of 1 is equal to psi 1 is greater than this t. Well, subtract 1 is 0. If t is here, then infimum of n such that s psi of n is greater than this t is 2, because psi 1 plus psi 2 is strictly greater than this number, and psi 1 is less than or equal. So this infimum is 2 here, and subtract 1, so we get 1. Okay, so in some sense, so this is just not, so let's use notation that n lambda of t is inverse of psi of t, so generalized inverse as psi of t, and minus 1. On the previous lecture, we discussed some inverses of random walks of stochastic processes and convergence of processes and their inverses, or functions and their inverses. And the first question I wish to discuss is, what is the limit behavior of Poisson process as t goes to infinity. And okay, let me write like lemma. The first statement is this. For every lambda, n lambda of t divided by t converges almost surely to lambda as t tends to infinity. This is a law of large numbers. Well, if t is a natural number, then this statement is trivial. Indeed, what is n lambda of n over n? This is the sum of increments. And each increment has Poisson distribution with parameter lambda times the length of this time interval from k to k plus 1, which is 1. So by the law of large numbers, we have convergence to expectation of this, and expectation of Poisson distribution is lambda. But here, the statement is about continuous parameter t, and we may estimate n of t over t. From below, we take integer part plus 1, and n of integer part of t is less than or equal to n of t. And upper bound is we make numerator greater and denominator smaller. Now I want to apply this law of large numbers, so I multiply and divide. And I know that this part converges almost surely to lambda, and this divided by this converges to 1. So the right-hand side converges almost surely to lambda. It's easy to show that the left-hand side converges almost surely to lambda. Hence, n of t divided by t converges to lambda almost surely. Well, another question is, okay, we have almost sure convergence, and what about convergence of certain scalings? For example, let us consider this process. So we scale time n times and space also n times and ask ourselves what is the limit. Well, if we denote if t is fixed and this is s, then we may multiply by t numerator and denominator. So n lambda of s divided by s converges to s times t. Oh, this converges to lambda and times t. So for any fixed t, this process converges to lambda times t. The question is, do we have uniform convergence to lambda t on every interval? And the answer is yes, it is. This is true. This is true. And the proof. I will use the following well-known statement from mathematical analysis. Maybe we discussed this statement a week ago. And the statement is this. Assume that Fn be a sequence of non-decreasing functions. On 0t. And assume that Fn converges in each rational point to a non-decreasing and continuous functions. That for every t from 0t, intersection with rational numbers, we have pointwise convergence. Where f is continuous. Then this sequence Fn converges uniformly to f as n tends to infinity. And now, what are we doing? This is a sequence of non-decreasing functions, Fn. This is a continuous function f. We know almost sure convergence for every fixed t. So we can select a set of, for every t rational number, we can select a set of probability 1, omega sub t, such that Fn of t converges to f of t for every omega in omega t. Hence, we have convergence Fn of t. We have convergence Fn of t to f of t for all t rational numbers and for all omega in intersection of omega t. And since this set is countable and probability of each omega t is 1, then probability of this intersection is also 1. So on this set, we have pointwise convergence. So by this lemma, we have uniform convergence Fn to f. Well, we proved the uniform convergence of this process to this linear function. Okay, questions? If not, then the last important fact that the process, Poisson process with intensity lambda has the following scaling property. It has the same distribution as Poisson process with intensity 1, but we take time lambda t. Well, it's very easy to prove, for example, using the definition. This process has so this process has is non-decreasing, obvious. Independent increments also obvious. Stationary increments, yes, it is. What do we need to check? That the distribution of n lambda t, say, is Poissonian with parameter lambda t. Yeah, this is also true because the parameter is 1 times lambda t. Well, and we also can consider this process and process with another intensity mu, and the result is this, that this process has the same distribution as this one. And maybe the last property for today, and we finish our lecture, that if you have two independent Poisson processes with intensities lambda and mu, then their sum is also Poisson process. And what is intensity?
Lambda plus mu.
Yes, lambda plus mu. Indeed, the proof of this fact is also follows from the definition. This process is non-decreasing. This process have independent and stationary increments because these two processes are independent and have this property. The only thing is to find distribution of increment. And we know that some of independent Poissonian random variables also has Poissonian distribution, and we add parameters. So that's all. And next time we will discuss don't-scale scaling limits for example, for Poisson process. For example, we may subtract expectation, divide by variance, divide by square root of lambda, and ask ourselves what is the limit of this sequence. And well, if you apply the central limit theorem, or if you use characteristic functions, then you may see that for every fixed t, the distribution here will be Gaussian. And look, all these processes have independent and stationary distributions. So probably the limit here is a Gaussian process with independent and stationary distribution. So the question is it Brownian motion or not? And we will prove yes, and we will discuss a lot of models on this topic. Okay, that's all for today. Thank you for your attention.
Thank you.
Okay, see you
Thank you.
next week.
Thank you. Goodbye.